Is screen visible?
Yes, sir.
Okay, so what we were discussing last time, the location of root theorem. What this theorem says ki f is continuous on closed and bounded interval. And f of a into fb is negative, so the values of function at a endpoints have opposite sign. Means what? F of a is negative and f of b is positive, or f of b is negative and f of a is positive. Then what happens? There exists c in between a and b, which is the root of function. Right, this is what we saw. So also we discussed the proof. So what the geometrically this theorem says, if at a function is positive, then at b it is negative, or vice versa. If function is negative at a, then it is positive at b. Then the graph of this function intersect x-axis somewhere. That point is c, and at that point c, well, y coordinate is 0, so f of c is 0. So first proof we discuss is a bisection method. That means what was the steps? First, divide interval AB into two equal parts. Midpoint is P1. If P1 is a root, then we'll take it as a root. Otherwise, check the value of f of P1, right, positive or negative. Accordingly, you can choose your next interval I2. So in this particular figure, f of P1 is negative, so root lies in between A and P1. Divide it into two equal parts. Midpoint is P2. Now which interval will accept? P1, P2 because the root lies in between P1, P2. Then again divide into two equal parts. Midpoint is P3. So continue this process P1, P2. Right. This is a sequence. So Pn is a sequence. So if c is equal to limit of Pn, then f of c is 0. So actually the sequence converges to the root of this. Now what is alternative proof? So alternative proof is, so our assumption is our interval is closed and bounded, and whatever is the situation, at a function is positive, negative, at b function is positive. So a f of a function may have many roots, right? So do you see the second figure? Yes.
Yes, sir.
So this function has three roots, right? It intersects x-axis, graph intersects axis at 3 points. It has three roots, but location of root theorem guarantees there is at least one root in between a and b. Above conditions are satisfied. So in general, function can have many roots, but at least one root is there if conditions are satisfied. So in this figure, if you look at the in this figure, if you let A is equal to set of points x belongs to AB, such that f of x is negative, right? If you look at the set of points at which f of x is negative, right? Now, do you understand in this figure which set has what is the set A, or what are the points at which function is negative? Yes.
Yes, sir.
So this black color, right? Do you see the black color? These points, right? So therefore, from this figure, you observe that basically this is set A. These points, because every point in this black color region, they satisfy the condition that f of x is negative. So now what do you expect? Is it is so then it is a subset of interval AB, correct? Therefore, A is bounded, correct? A is bounded. Now, what is the guarantee that A is non-empty? What is the guarantee A is non-empty? Yes. So why this set is non-empty? Can you tell me at least one element in this set, irrespective of this graph, from the conditions in the statement of theorem? Yes.
f of a, f of b less than 0.
No, f of b is not less than 0. In particular, so suppose f of a less than 0 less than f of b. Suppose value of function at a is negative, because our basic condition is, what is our basic condition? So the sign of fa and fb is opposite, means one is positive, another is negative. So suppose f of a is negative and fb is positive. so see, at least a is a member of set A, because for the function value of function at A is negative. So A is a member of A. So this set A is non-empty. At least one member is there. Correct? Is it clear what I am saying?
Yes, sir.
Right. So this set is non-empty bounded. So by completeness property, what I should say? Supremum of A exists, right? So let C is equal to supremum of A. Suppose C is a supremum of A, then is C member of interval? Is C belongs to I? Yes.
Yes, sir.
Right. Then C belongs to I. And from this figure, what is a C? What is the supremum of this? From this figure, what is C? C is this point. Correct? Supremum of this set, largest element. So largest element or supremum is C of this set. So, and second thing is key C is and what is the value of function at C?
0.
0.
0. And why? Why? So you need reasons, and these two things are not easy. So you just try to prove it. Not easy, not straightforward. Later on, if we get time, we'll try to prove this. But this is idea key how to get a root. So ultimately, what we get if you are able to prove that C is a member of I and f of C is equal to 0, then what we found ultimately there is a C, that is there exists C belongs to AB such that f of C is equal to 0, and C cannot be equal to B because f of B is positive. But anyway, so the main point is, can you prove C belongs to I? Can you give the arguments to prove that C is a member of I and f of C is 0? That's it. You just uh, try to prove this. The strategy is this. Where is this? How to fill up the gap? You should think about it. So I gave you two different proofs. So first proof also we'll discuss in detail later on, but yeah. So is this clear? What is location of root theorem? It is clear.
Yes, sir.
Now, now we want to extend this idea further. Suppose f is a function defined on some interval a b to r, right? So f is defined on some interval a b. Now, so a b. Suppose value of function at a is some number. So a b. Now value of function at a is some number, let us say f of a, and value of function at b is some another number f of b, right? And if I choose some k between f of a and f of b, is it possible that there exists some c at which value is k? Is it possible? So if
If f is continuous.
right, so if f of a is less than k less than f of b, then does there exist C belongs to AB such that f of C is equal to K? So this is a question. That means if you have f of A and f of B, will the function fill up everything between f of A and f of B? Will function fill up anything between f of A and f of B? This is a question, right? So let us see example. Suppose I take f of function f defined on minus 1 to 1 to r. So f of x is equal to 1 if x greater than 0 less than 1, and minus 1 if minus 1 less than x less than 0. So if you see the graph of this function, so minus 1 to 1, domain is minus 1 to 1. So minus 1 to 0 function is minus 1, and 0 to 1 function is 1, right? So what is f of 1? So what is the value of function at 1? I have defined it at 1 to be 1. And what is value of function at
1.
minus 1? And what is the value of function at -1?
-1.
Minus
minus
1.
1.
Now you check that key half lies in between -1 and 1, right? That is f of -1 less than half less than f of 1. This is a k actually. So this is a number k which lies in between f of a and f of b. So a is -1 and b is 1. So, but there is no. Does there exist some number c in the interval -1 to 1 such that f of c is equal to half? Does there exist a point in domain at which value is half 1 by 2? Is it true?
No.
Yes,
No, sir.
no. And why this is not true? Because this function is not continuous. Right, and therefore, in general, the above of a previous question, if k lies in between f of a and f of b, there is no guarantee ki there is a c which attain the value k, right? At which function will attain the value k. So, so there is no guarantee of having such c if function is not continuous, right? So that is our next theorem. So Bolzano's intermediate value theorem. So what this theorem says, he let I be an interval let f from I to R be a continuous function on I. So I is any interval, right? So if a and b two numbers in I and k is a real number such that f of a less than k less than f of b, then there exists c belongs to I. There exists c belongs to a and b such that f of c is equal to k. Okay, now try to understand the statement carefully. So what is given? I is interval. No matter what type of interval it is, closed or bounded, doesn't matter. It is just interval, whatever is interval I. In that, look at AB. A and B are any 2 points in I. Now function is continuous on this interval I. So function is continuous function on this interval I. Now value of function at A and value of function at B. So this is graph of f on I. And now look at value of function at A. So fa, value of function at B is f of b. Do you see the figure?
Yes.
Right. Now k is in between f of a and f of b. Then there is, if you draw a horizontal line passing through k, then it intersect x, the graph of function at some point, and draw a vertical line. Look at the point C. Then what are the coordinates of a point on the curve C comma f of C? But what is a y coordinate of C comma f of C is actually k, because if you look at horizontally, then f of C is basically y coordinate and it is k. So this is actually situation. But what are the conditions here on interval, right? So domain of function is interval, and you choose any two values of function, then it will cover everything between f of a and f of b. Whatever k you select, it has a preimage. This is very interesting thing. So later on we'll see examples where these things fail, but conditions are essential: continuity and interval, right? These are two important assumptions. Function is continuous, domain is interval. Then you choose any 2 points in the range, function will fill up everything between that. Correct? So statement is clear. Statement is clear.
Yes.
Yes. Now, using the previous theorems, we'll try to prove this, and proof is not really difficult. So what is given data? I is an interval. I is an interval. Second, f from I to R is continuous. Third thing, AB belongs to I, right? And f of A less than K less than f of B. So what is our claim? What is our claim? There exists C between A and B such that f of C is equal to K. Basically, C lies in between A and B. So situation is clear. What is given, what is hypothesis, and what is the conclusion we want to make. Suppose A and B are any 2 points, and value K lies in between f of A and F. So assume that so A and B are two numbers. One of them is bigger, another is smaller. So suppose A is less than B, right? A is less than B. So now define. Suppose A is less than B. Then can I say that F is continuous on closed interval AB? Is it true? See the figure. Function is continuous on bigger interval I, and A and B are some points, and then look at the interval A to B. Can I say that F is continuous on AB, interval AB, closed and bounded interval AB?
Yes, sir.
Right. So F is continuous, no doubt, because F is continuous on bigger set. So now define G on AB to R. I am defining new function by, so G of X is equal to Fx minus K. Right, so I have defined new function on closed and bounded interval fx minus k. K is a constant, right? And fx is our drain. Domain of G is a closed and bounded interval. Is it true?
Yes.
Right. Second point, G is continuous on this interval AB. Is it true?
Yes, sir.
Do you agree? Why it is continuous?
Because f of x is continuous and k is constant function. So their
Very good.
algebraic sum is continuous.
Correct. So fx minus k is certainly continuous because it is difference of two continuous functions. Third point, what is g of a? What is g of a? Is fa minus k. But where is, so fa is less than k. So what is fa minus k? Is it negative?
Yes, sir.
Right. So g of a is negative. What is g of b? fb minus k. But f of b is greater than k by our assumption. Right? We have chosen k between f of a and f of b. So this is positive. Right? That is g of a less than 0 less than g of b. So therefore G satisfies conditions of location of root theorem. Right. So what is the conclusion?
There must exist C such that f of g of c is equal to 0.
Therefore, by location of root theorem, if all these conditions are satisfied, then the conclusion of location of root theorem must hold. Right. So there exists C belongs to A and B such that G of C must be 0. That is, but what is G of C? F of C minus K is equal to 0. That means F of C is equal to K. Thus, there exists C belongs to AB such that F of C is equal to K. So, is this clear? Yes.
Yes, sir.
Yes, sir.
So, so proof is very straightforward, just application of location of root theorem. Now, if function is continuous, then it is true. Suppose I define a function on 0, 1, union 2 to 3 to R. So f of x is equal to f of x is equal to x plus 1 if x is in 0 to 1 and is equal to x square plus 5 if x is in 2 to 3. Now my first question is f continuous on this set? My set is this 0, 1 union 2 to 3. Is this function continuous?
Yes, sir.
Yes, fine. Now can you sketch the graph? Why this function is continuous? On 0, 1 it is x plus 1, it is continuous on 0, 1. On 2 to 3 it is continuous, and therefore on union it is continuous. By which theorem or lemma which we
Yes,
discussed before? Pasting lemma, right? On each separate part it is continuous, and on intersection there is no intersection, so no problem with intersection. So on intersection intersection is empty, so f is continuous. Now sketch the graph. Right, so while learning calculus, you should always draw the graphs. While studying calculus, try to draw the graphs. That will make your understanding simple. So 0 to 1, x plus 1. So how is the graph x plus 1? Right, 0 to 1, this is a graph. line y is equal to x plus 1, but for 0 to 1.
Sir,
Yes.
your screen is frozen.
Yeah. Up to which line you can see?
It's visible now.
Yeah, means it takes some time. Okay. Do you see the figure?
Yes, sir.
What is the graph for interval 2 to 3? At 2, what is the value of function? 9, right? And what is the value of function at 3? 9 plus
14.
5, right? And it is square function, x square plus 5, so it is curve. Here 0 to 1 it is a stand, here it is, but this function is continuous because 1 to 2 part is not in our domain, so we should not worry about it, right? So f is continuous, no problem. Question 3. Now half a is equal to half and b is equal to 5 by 2. These are points of a function. Is it true? Yes. What is f of a? Is f of half. So half plus 1 is 3 by 2. What is f of b? F of 5 by 2. So 5 square by 2 square plus 5, which is 25 by 4 plus 5. So what is it? 45 divided by 4. Correct? Now if I take k is equal to, so half is here and 5 by 2 is here. And what is the value of function at 5 by 2? So this is b, this is a, it is f of b. So, and what is f of half? F of a is here. So now if I take k is equal to, for example, 4, then can I say that f of a is equal to 3 by 2 less than 4 less than 45 by 4, which is f of b. Is it true? 4 lies in between f of a and f of b if a is 1 by 2 and b is 5 by 2. Is it true?
Yes, sir.
Right.
Yes.
Now, does there exist C belongs to domain, in the domain, and C is in between A and B, such that f of C is equal to 4. Is it true?
No, sir.
No, because I have, if you look at the graph, I have chosen 4 here, but for 4 there is no pre-image at all. For 4 there is no pre-image. And why this problem arises? Because why theorem fails here? Means conclusion fails. Why conclusion of theorem
Domain of the
fails?
curve.
Right. So here domain of f is not an interval, and therefore continuity and domain is interval is essential. Right. So from this theorem we can extend some result more. So let I is equal to ab be a closed and bounded interval. And so suppose f is a function, is a continuous function. Right, suppose f is a continuous function. So, okay, now what is the situation? Let me sketch the graph and then you can. So my domain is now interval and function is continuous. So this is my function of a graph of function f on this interval AB. So, okay, so this is a graph of function f. Do you see the figure? Now, do you see the point at which function has maximum value? And do you see the point at which function has minimum value?
Yes, sir.
So at this point, function has minimum value. So you can see that there are 2 points. Let us say alpha and beta. So f of alpha and f of beta. You see these 2 points. But what is f of alpha actually? Minimum of f of x. And what is f of beta? Is maximum of f of x. This is actually the situation. Now, do you understand? Suppose I choose any k between f of alpha and f of beta, right? Then does there exist c at which value is k from this figure?
Yes, sir.
Yes, sir.
Right. So, in fact, there are 3 values of c possible. Do you understand? There are 3 possible. C1, C2, C3. There are 3 possible values of c for this k. Right, at which value is k. So what is my statement of theorem? Ki if a domain is closed and bounded interval, function is continuous. So if k is a real number such that infimum of f of I less than or equal to k less than or equal to supremum of f of I, right? K lies in between supremum and infimum of range. Then there exists c belongs to I such that f of c is equal to k. In fact, there may be more than one values of c for at which value is k, but at least one c is there. And this from this figure it is clear. If you choose any k between this, then it is true. So how to write down the proof? How to write down the proof? So what is given? What is given? Domain is a closed and bounded interval. Correct?
Yes.
Second condition, f is continuous on this domain. And therefore, if you are given anything between supremum and infimum, so from this assumption, by location of root, by maximum minimum theorem, max mean theorem, by max mean theorem, what happens? Are these conditions same in the max mean theorem?
Yes, sir.
And so by max mean theorem, what we can say?
It has absolute maximum and absolute minimum value.
Right. So there exist alpha and beta in this interval AB such that f of alpha is equal to supremum of f of I. F of I means range or maximum of f of x, and f of beta, whichever is alpha, whichever is beta, doesn't matter. But in the figure, I should say that which is alpha and which is beta. So So f of beta is equal to infimum of range, or it is minimum of f of x, because maximum element exists if it is a member of range. So maximum, it is also supremum if maximum element exists. So supremum or maximum element, infimum or minimum element, same in this case. Why? In general, supremum and maximum element may not be same, but in this case, it is true because what? Because supremum is member of set. Why it is member of set? Because there is a alpha at which value is attained, and therefore it is part of range, and so it is maximum element. Correct? Correct. Yes. So is it clear what I am saying?
Yes, sir.
Yes, sir.
Okay. Now what is the situation? At alpha value is maximum, at beta value is minimum. Now see the figure. So thus alpha and beta are in AB. F of alpha is maximum of f of x. F of beta is minimum of f of x. So now let k is a real number such that maximum of f of x or supremum of f of I is less than or equal to k, is less than or equal to infimum of f of I. Then f of alpha, so k lies in between supremum and infimum means what? Means what? F of beta less equal k less equal f of alpha. See, if f of alpha is equal to, if either f of beta is equal to k or f of alpha is equal to k, then nothing to prove, right? Because we got the point at which value is k. So if either f of beta is equal to k or f of alpha is equal to k, then nothing to prove, correct? But if neither f beta is equal to k nor f alpha is equal to k, then we want to investigate further, right? Then f of beta is less than k less than f of alpha. But by Bolzano's intermediate value theorem, what we can say, k lies in between f beta and f alpha, and f beta and f alpha are two members of domain. What that theorem says ki if your function is continuous on any interval I and a and b are 2 points at which uh, in interval, then k lies in between fa and fb, then it has pre-image, right? So there exists c belongs to what? There exists c belongs to I or alpha beta or beta alpha, whichever is smaller, or c belongs to I. Same thing, such that f of c is equal to k. So is it clear? Does this prove our
Yes,
conclusion?
sir.
So that is there exists c belongs to domain such that f of c is equal to k. Right. So provided function is continuous, domain is interval, then function attains everything between supremum and infimum. It will not happen that key function will miss out anything between supremum and infimum. Whatever k you select between, it has a pre-image. So what does it mean? So if conditions of corollary are satisfied, right? If all above conditions are satisfied, then f attains every value between supremum of f of I and infimum of f of I. So this sentence is very important. If your function is defined on interval AB and you know that some number is infimum of f of I and some another number is supremum of f of I, then whatever is k you choose, it will fill up everything. That means you go back and see there is c. That means you choose any number between supremum and infimum, it will be completely filled up by images of values of function. What does it mean? Ki, so can you characterize the domain of code range of function? Can you characterize range of function? Right, we want to characterize range of function. Characterize in the sense ki is range of function always interval? Is the range of function always interval? What is the interval? What is let I subset of R? Then I is an interval if when we say that some set is interval
When two elements belonging to the set, we take two elements belonging to the set and all the terms between them are included in the set.
Right. For any xy belongs to I, the segment xy. What is the segment actually? All x to y is totally contained in I. So this is actually the basic definition of interval. Means some set is interval means what? You choose any two elements x and y from that set, join them by line segment. That total line segment remains inside the set. Then it is interval. Otherwise, it is not interval. And then from the previous corollary or theorem, if you look at supremum of fi and infimum of fi, function fill of everything in between. Means what can you say about the range? What can you say about the range of this function?
It is an interval.
Interval. Do you observe this easily from this figure? So, and what is the initial point of interval and what is the end point of the interval?
F of beta and f of alpha.
Right, supremum and infimum under this setup. So that is very interesting. So you look at the function f. Suppose I define a function from 0 to 2 r, and f of x is equal to x less than 1, and x plus 4, 1 less than x less equal to. Now can you sketch the graph of this function? I have defined a function from 0 to 2. Right, 0 to 1 it is x. Now from 1 to 2 it is x plus 4. That means at 1 value is 5. And okay, let me draw some bigger figure. So 0 to 1 it is same as x, and 1 to 2 it is x plus 4. Right. So what is my domain here? So what is my domain here? 0 to 2. Right. Now what is my range f of I? Can you tell me range?
0 to 6.
0 to, does
6.
it contains 3? Is 3 in the range?
No, sir.
No, sir.
So what is it?
0 to 1 union 5 to 6.
Right, 0 to 1 union 5 to 6, and this is not interval. So range is not interval, domain is interval. What is the problem? Why this happened?
Function is not continuous.
F is not continuous on 0 to 2. In fact, it is not continuous at 1. So ultimately it is not continuous on 0 to 2, and therefore the range is not interval, even the domain is interval. Right. Even domain is interval, range is not interval. And if you look at the previous example, if I define a function on 0 to 1, union 2 to 3, right? So what is f x? So x, the x if 0 less equal x less than or equal to, and x minus 1 if 2 less equal x less than or equal to 3, right? Now sketch the graph. Sketch the graph. So 0 to 1 and 2 to 3. So 1 to 2 is not in the domain. 0 to 1 it is same as x, and what is the value of 2 is again 1, and 2 to 3 is again x minus 1, right? You check the graph whether it is correct. Now what is the range? Here domain is 0 to 1 union 2 to 3. What is the range of f? What is the range?
0 to 2.
It is 0 to 2. Is it correct? And it will attain every value between 0 to 2. Can you prove this? It is not very difficult. It will attain anything between 0 to 1. It attains 1 at 1, and at 2 value is 1, so it attains 1 again, and it attains everything between 1 and 2. So it attained everything between 0 and 1. It attains everything between 1 and 2. Also it attains 1, 0, 2. So the range is, even domain is not interval, range can be interval. Do you understand?
Yes, sir.
But sometimes it may happen that key domain is not interval, range is also not interval. That is also possible. You can just modify the function on the same set, right? So g of x is equal to x, and it is x plus 4. So here domain is not interval, range is also not interval, that you can check. And therefore, so if so, what is a what this example suggests? Ki even domain is interval. If function is not continuous, range may not be interval. That is first observation. What is second observation? Even domain is not interval, range can be interval. And what G suggests, even domain is not interval, range may not be interval. So that if domain is not interval, range may not be interval, right? If function is not continuous, then range may not be interval, maybe or may not be interval. So therefore there is uncertainty. So what is a certain thing? What is a certain thing? So certain thing is, let I is equal to AB a closed interval. So suppose f from I to R is a continuous function. Then the set or range of f of I is equal to the collection of images, is a closed and bounded interval. Right? Then range is a closed and bounded interval. Not only interval, it is closed and bounded interval. Under what assumption? Domain is closed and bounded interval. Function is continuous. Statement is clear?
Yes, sir.
So what is given? Domain is closed and bounded interval. What is second thing? F on I to R is continuous. Then what is our claim? What is our claim? F of I is a closed and bounded interval. So that is f of I is some interval CD. Right? F of I is some interval, closed and bounded interval CD. But if you recall our previous discussion, I is closed and bounded interval, and so what is supremum and infimum? So since so all the conditions of max min theorem are satisfied, right? So can we apply max min theorem?
Yes, sir.
Yes, sir.
Right? There exists alpha and beta in interval I such that f of alpha is equal to supremum of f of I. Let us call it as capital M, and f of beta is equal to infimum of range. Let us call it as small m. And therefore, what is our claim? What we should claim? So we claim that what we claim, the range is actually interval small m to capital M. Right? See, what is the range now? Range cannot be larger than capital M, smaller than small m, right? And we claim that key exactly range is exactly interval small m to capital M, supremum to infimum. Correct? Do you agree? And proof is very straightforward. So note that small m and capital M are in the range. Do you agree?
Yes, sir.
Yes, sir.
And if you does range occupies everything between small m and capital M? Does
Yes.
range, right? Now if m less than k less than capital M, then by intermediate value theorem,
There exists C such as f
there
of c
exists
equals
C
to k.
belongs to I such that f of c is equal to k. That means k, if you choose anything between small m and capital M, there is C in domain at which value is k. That means k is in the range. Do you understand? It
Yes,
Yes.
sir.
means thus for every k belongs to m to capital M, k is in range. So can I say that small m to capital M is contained in the range of I, in the range?
Yes, sir.
Also for every x in I, small m and f of x. For every x in the domain, the value of function lies in between supreme and infimum. That means for every x in I, f of x belongs to small m to capital M. What does it mean? For every x in I, f of x is in between, right? For every y in f of I, can I say that y belongs to small m to capital M? Is it true that the range is contained in small m to capital M?
Yes, sir.
And therefore,
Yes.
what is the conclusion of this? Hence, range is actually the interval infimum to supremum, and therefore range is also closed and bounded interval. Right. So our basic assumption was function is continuous, domain is closed and bounded interval. Okay, so we'll stop here. Next time we'll see the next part. Okay, we'll stop here.